Once the raw data was loaded into Spark data frame, we have to do some initial preparation. By example, remove some null values from columns, convert strings into timestamps, calculate certain columns based on the values of other columns, or convert strings into other data types. Under certain operations and not easily reproducible, it was observed some kind of network connection error while using the data frame loaded from Elastic. Also, very low performance was experienced during the initial attempts on modeling. Due to the previous problems, it was decided to load the raw data from Elastic into a data frame and directly save it as a local CSV file to then execute all the transformation. After reading the data from a local CSV file, we notice a performance improvement while transforming the data frame or even during the creation of the models. Initial model design, linear regression, decision tree regression, and random forest. Different approaches were tested to determine what to use as feature variables. By example, use of browser delay, network delay, and server delay to predict end-to-end and time to interact. Here, while doing the modeling, we got R-squares of 1 or sometimes negatives. Use of time series prediction approach by using Windows functionality. By example, by using the previous 5 to 10 values of the response time variable to predict the current variable. Here, by example, we experience a very low R-square under 0.3. Finally, the use of categorical values to predict end-to-end or time to interact, but also other response variables like client time, network time, server time show to be the most realistic way to do this prediction. Now, let me give you a quick demo of the correlation testing that was executed. Once we have PySpark running and we load some libraries, we can read the data from a CSV file. We prepare the data. Then we can run the correlation for TTI and all the other response variables. Similarly, we can run the correlation between end-to-end time and all the other variables. The reality is that the browser delay, network delay, and server delay, the three together create the end-to-end response time. So between the three, there is a one-to-one correlation, and they have a very close correlation with TTI, and that's the most probable reason why we were getting the R-square values of 1 or negative. Continue with the preparation for modeling. We have to do a few more things. Adjust null values mainly in the network tab feature. Reduce the number of columns to only those which are being used in the modeling. Remove the outliers based in IQA range as we did in EDA. Out of the 7 features that we pick for the model, 6 are categorical values, which with the use of the one-hot encoder estimator when converted into column or binary vector. To the previous vector, we also include a numerical feature, number of round trips, which shows the number of round trips per user interaction. To achieve the use of one-hot encoder estimator for 6 categorical values and the numerical value, we use a pipeline to create stages for each categorical value and then convert it into a single vector. The final data frame with the 6 response variables labels, the 7 features, and its vector representation was saved as a Parquet file. 3 different algorithms were used to compare and select the most accurate model: linear regression, decision tree regression, and random forest for regression. To fine-tune the model and compare the best setup for each of them, cross-validation was used. The function param grid builder was used in conjunction with cross-validator to fine-tune each of the algorithms. Each of the fine-tuned algorithms was used to train the model against 80% of the data from the first week of October. 5 models were created for each algorithm to predict time to interact, end-to-end time, client time, network time, and server time. Once the algorithm was trained, it was scored against the test data using root mean square, R square, and mean absolute value. When the result was calculated, it was stored in Elasticsearch, Let me show you a Kibana dashboard when the results were from multiple executions were stored. So here is the dashboard. In most of the cases, the decision tree had the highest score in R square and the lowest score in the root mean square and mean absolute error. Final model results, anomaly identification. Once we have stored in this the prediction models and the model to handle the categorical values as one hot encoder estimator, we can use the model and create rules to identify anomalies. By example, anything that is 20% above the predicted value will be labeled as an anomaly. Using the cross-validator model and the Python model, we can load the model from disk. Now we can retrieve the data from Elasticsearch, similar to what we did originally to create the model, but now to use the model to identify anomalies. Using the models, besides identifying anomalies, we can also calculate the degree of the anomaly. And finally, we can store back the results into Elastic. Scale out anomaly detection using machine learning models in Spark. In the test data set with over 22 million records, or from the actual productive data where we have an average of 1 million records generated by hour, we need to validate the scalability of the process with the use of Spark. By example, running this anomaly detection process in parallel in multiple nodes. With a small setup of 2 servers and 12 cores in total, we could process up to 22 records per minute. Once the anomaly data was loaded into Elastic, we can visualize the data to have an overall understanding of the daily anomaly and most common cause of the anomalies. Let me show you this Kibana dashboard. This dashboard shows an overall look of the anomalies for the second week of October. We can see the percentage of time to interact for anomalies aggregated every 3 hours every day. We can see the breakdown of anomalies in client time, network time, or due to server time. Or we can see the absolute value of anomalies versus normal interactions in a time series fashion. In a more detailed dashboard, we can see the total number of anomalies per tenant or per user interaction. We can use certain capabilities for Kibana to filter out the data. By example, selecting a tenant and a specific user transaction. With this, now we can use a heat map that shows the day of the week when we have the worst anomalies by client time, network time, or server time. Finally, we can identify the reason of a specific anomaly, either in this case server time or in this case network time. Problem statement. APM data is the perfect source of information to determine the end user experience while using a web application. Now, in the context of a SaaS offering, there are multiple implications and combinations which will affect the end user experience. By example, multi-tenancy. The same software is used but customized in endless number of ways and from different customers, causing different performance behaviors. Multi-client support. A cloud solution is expected to be used by different type of clients. By example, desktop applications, different UI versions, browsers, operating system, native and hybrid mobile applications. Network. A cloud solution is accessible over the internet. It is expected to be used from multiple locations around the globe under different network conditions. Application complexity. Large number of screens and actions to be executed within those screens cause a very high number of combinations and actions available within a SaaS application. Summarizing the problem and what is proposed. Problem statement. Due to the high number of combinations of factors that can affect the performance of a SaaS application and the high volume of data generated every minute, the use of traditional statistical approach is less than ideal for near to real-time identification of performance problems or anomalies based on user experience. Proposed approach. To use machine learning techniques on big data that can help us to identify anomalies in user experience and provide detail which offers potential reasons of what is causing the performance problems. Project architecture. As you can see, the data was extracted from an APM repository into Elastic using Python code. The initial EDA was done in Kibana using data from Elasticsearch, and a more detailed EDA was done using Jupyter. Finally, the modeling and the processing of the data was done in Spark, with Spark saving data back into Elasticsearch. Final notes. It was possible to create regression models to determine the expected numerical values for different KPIs using mostly categorical features, which represent over 80,000 different potential combinations and one numerical value. The use of Spark for anomaly detection after models were available allows to process high number of records with an observer value in average of over 22,000 per minute, which shows the capacity to process a million user interactions per hour, even in a small setup like the one that it was used during this project. Once the anomalies were detected for different response variables, we could actually use them in a practical way to determine the reason causing anomalies, or in this case, the reason of increasing response time. Using technologies like Elasticsearch could help us to have real-time visualizations and dashboards to identify problems in a SaaS application.